Hi everyone, and welcome to Introduction to Tensors in PyTorch. This video is the first in our series where we'll be implementing AlphaFold from scratch. Today we'll start with the fundamental building blocks of deep learning, tensors. We'll cover what tensors are and why they're fundamental in machine learning models like AlphaFold, how to create and manipulate tensors in PyTorch, and also some advanced topics like access-wise operations, broadcasting, and the powerful torch.einsum function. Everything we discuss today forms the rest of the series. You'll apply these concepts directly in the Jupyter notebooks that accompany each video, where you'll build AlphaFold piece by piece. So, let's dive into tensors and take the first step towards unraveling the mysteries of protein structures. Now, the best part about tensors is that while the name might be new to you, you've probably worked with tensors before. Vectors, for example, are one-dimensional tensors. Matrices are two-dimensional tensors. Operations like the dot product between vectors or matrix vector multiplication are classic examples of operations on tensors. Tensors are a generalization of this. A tensor is an n-dimensional array. Going beyond 2 or 3 dimensions might sound a little odd or technical, but it actually comes up really naturally. If you start off working with black and white images, like we'll do when classifying handwritten digits in the tutorials, you're totally fine with 2 dimensions. Black and white image is basically a matrix of values between 0 for black and 1 for white. You can specify a row and a column and access the pixel value at this location. If you think of a colored image, however, at each pixel there already are 3 values, the amount of red, green, and blue at the pixel location. At each pixel we have a feature vector consisting of 3 values. The whole image is a feature volume, a 3-dimensional tensor of shape HWC, where h is the number of rows or the height of the image, W is the number of columns or the width of the image, and C is the number of channels, in this case 3. To get the redness of the top left pixel, we'd index into the image like image at 0, 0, 0. But 3 dimensions often aren't enough. In machine learning, we're usually working with batches of data. For example, we might compute the forward path through our model for a set of n images of different dogs. Now, we need a 4-dimensional tensor of shape NHWC to process all the images in a joint fashion. This is the typical form of tensors in machine learning, a batch of feature volumes where the dimensions of the feature volume have actual semantic meaning, like the location in the image and the color channel, and the batch dimension is just being carried along in a for-each manner. So, this is what tensors are, but what is PyTorch? PyTorch is a machine learning framework, and at the core it has 2 tasks. First, it needs to implement a multitude of operations on tensors, like matrix multiplication, and it needs to do so very efficiently. You may have worked with NumPy before, which basically does the same thing. PyTorch, however, can be orders of magnitudes faster, as it can harness the power of your graphics processing unit. The second task is a little less obvious, and it's called automatic differentiation. We'll take a closer look at why this is so important in our intro to machine learning, but basically, training a machine learning model is about minimizing the error of your model. And the way that this is done is by computing the derivative of the error with respect to every single parameter in your model. Knowing the derivative, we know in which direction we need to change the parameter to decrease the error. And this is the whole magic of machine learning. Calculating these derivatives by hand is cumbersome and error-prone, and luckily, PyTorch does it automatically. So, to sum up, tensors are n-dimensional arrays, which can represent everything in machine learning, from the images, or in AlphaFold's case, sequence alignment data that we feed into a model, to the predictions it outputs. PyTorch's job is twofold. First, to provide efficient operations on the tensors, and second, to automatically calculate the derivatives needed for learning. With these foundations in place, let's dive into how we create and work with tensors in PyTorch. The simplest method for tensor creation is torch.einsum. It takes a nested list as an argument and creates a tensor of the same shape. Most of the time, you'll use this syntax to create a vector or a matrix. The first line here creates a 4-element vector. The second line creates a 3x2 matrix. You can see that the outer pair of brackets has 3 elements, while the inner ones have 2 each. This is where the tensor has shape 3, 2 and not 2, 3. You can use this syntax to create any shape of tensor. Here, for example, we create a 4x1 tensor. This concept of 1 dimensions is really important. Even though the tensor has the same values as the 1-dimensional vector above, it has significantly different properties when used in tensor operations. There are some other important tensor creation routines that we'll get to know better in the tutorials. Torch.linspace, for example, is a method that's used very often. It creates evenly spaced values between a specified start and end. Here, we create 5 values between 0 and 2. Another important method is torch.once, which takes a desired shape and creates a tensor of this shape where every value is 1. You can scale this tensor to any other value. Here we create a 4x3x4 tensor of 5s. Tensors support most basic operations like plus or minus, but also logical operations like greater than, less than, or equal to. For example, the comparison of these two vectors, 3, 5, 1 less than 4, 5, 8, returns the Boolean tensor true, false, true. As we can see here, tensors can have different data types, like long for whole numbers, float for fractional numbers, and bool for booleans. You can cast a tensor to a different type. We can cast a Boolean vector back to floats, for example, which would return 1, 0, 1. One of the most important concepts for tensor manipulation is understanding the shapes of tensors and how we change them. To properly understand reshaping, we need to understand how a tensor is stored in computer memory. Although we are defining a tensor with a specific n-dimensional shape, in reality all tensors are one-dimensional, a sequence of all the values in a tensor. If we have a 3x4 matrix, for example, this is a 12-element one-dimensional tensor. And understanding how reshaping works is understanding how this flattening process works. By default, PyTorch uses a row major order. This means that elements that are next to each other in a row are also next to each other in the flattened 1D version of the tensor. The one-dimensional version is constructed by taking all the rows and concatenating them. This also means that the element one row further down has an offset of W to our element, where W is the number of columns of the matrix. This generalizes to more than 2 dimensions. Let's say we have a batch of matrices with shape NHW. Flattening this tensor means flattening all individual matrices, which will have shape H times W when flattened, and then concatenating them. Regarding the order of the dimensions, batch, row, and columns, flattening happens from right to left. We first go through all the different columns before jumping to the next row. For that, we go through all the columns again, go to the next row, and so on. After we are done flattening all the rows, we go to the next matrix in the batch. A proper understanding of this flattening process makes it easy to understand the concept of reshaping. Reshaping means going to the flattened version of a tensor, then changing the subdivision. Let's look at an example. We start with a 2x3 tensor. Its flattened version looks like this. If we are reshaping it to shape 3x2 now, this means that we are only taking 2 elements for each row, so the rows are 0, 1, 2, 3, and 4, 5. The full tensor now looks like this. This use of rearrangement reshaping is not the most common. More often, we'll use reshape to flatten some dimensions, like reshaping NHW to NH times W, or for unflattening, which is just the reverse. A common use case for reshaping also is adding 1 dimensions. In addition to reshaping, indexing and slicing are fundamental tasks when working with tensors. Indexing is about accessing an element at a specific position in the tensor. If we have this matrix, for example, and we wanted to access the element 3, we'd index to it using A at 1, 0, as it is the second row, index 1, and the first column, index 0. One thing to note is that when indexing elements in PyTorch, you don't directly get the elements as numbers, but as one-element tensors. This is because PyTorch wants to keep track of values in its specific format, for example, to allow for automatic differentiation. If you want to access the actual value as a number, you'll need to write this as a at 10.item. Slicing lets you extract specific portions of a tensor. Let's look at an example we'll meet again in AlphaFold. In the structure module, we'll come across the need to represent transforms, which are 3D motions, and consist of a rotation and a translation. They are in the format of 4x4 matrices as shown here. R is a 3x3 rotational matrix, and T is a 3-element vector. If we want to crop the 3x3 matrix from this transform, we'd index it as R is equal to T at 0 up to 3, 0 up to 3, to specify that for the rows and columns, we want to go from index 0 inclusive to index 3 exclusive. Starting at 0 is the default, so we could rewrite this as R is equal to T at up to 3 up to 3. For the translation, we want the first 3 rows, but only the 4th column. We can write this as T is equal to T at up to 3, 3. As the 4th column is the last column, we could also write this as T is equal to T up to 3 minus 1, using negative indexing. With this syntax, T would be a one-dimensional tensor. But we might want to concatenate R and T again later into a 3x4 tensor. For this, R and T would need the same number of dimensions. R would be a 3x3 tensor and T a 3x1 tensor. To achieve this, we could also use slicing in the following way. T is equal to T at up to 3, 3 to 4. Or T is equal to T at up to 3, 3 onwards, as going to the end is the default. This pattern of using one-element slices, like 3 to 4, is common to conserve one dimensions. Now, we might not work with a single transform T of shape 4, 4, but with a batch of transforms of shape n4, 4. Or we might even have one transform for each backbone in the batch, so we would have shape n-res 4, 4, where n-res is the number of residues in the proteins. To account for this, PyTorch provides the ellipsis operator, which is really useful. It expands to as many columns as are necessary to match the dimensions. The syntax r is equal to t at ellipsis up to 3 correctly extracts the rotation matrices. For the batched case, the ellipsis would expand to 1 column. For the double batched case, it would be 2 columns, and for non-batched use, it is omitted. As a last note on indexing, we'll talk on left-hand side and right-hand side indexing. The terms left-hand side and right-hand side refer to the left and right side of an equal sign in programming. So far, we've only used right-hand side indexing, where we index to access a slice of a tensor and assign it to a variable or process it further. Left-hand side indexing works just as well. Let's say we have a 3x3 tensor A and we want to replace its middle column with the tensor 0, 1, 2. We can do that like this. Here we use left-hand side indexing to select the slice of A and assign new values to it. This also works with all other indexing techniques. So far, we've covered the basics of tensor creation, indexing, and reshaping. These are the building blocks that you'll use constantly. But as you work with more complex data, you'll need more advanced tools, and one such tool is access-wise operations. Let's say you have a 4x3 matrix and you want to sum up the elements. You have 3 different options: summing up all the rows, resulting in a 3-element tensor, summing up all the columns, resulting in a 4-element tensor, or summing up all elements, resulting in a 1-element tensor. You can specify the behavior by setting the dim argument in the method torch.sum. If set to dim equal to 0, summation will happen along the row dimension. If set to dim equal to 1, summation will happen along the column dimension, and if set to none, all elements will be summed up. You can also set it to a tuple. Let's say you had a batch of matrices of shape n4, 3. You can calculate the sum of all elements for the matrices individually as torch.sum of A with dim equal to 1 and 2, or with dim equal to -1 and -2 using negative indexing, resulting in an n-element vector. There are many such operations. With torch.argmax, you can compute the index of the largest element. With torch.mean and torch.standard, you can compute the mean and standard deviation, and with torch.linarg.vectornorm, you can compute the standard L2 norm along a dimension. All of these examples are reducing. That means that the dimension you specified as dim will be missing in the output shape. You can set the parameter keep dim equal to true to keep it as a 1 dimension. This can be really useful, for example, to allow for concatenation or broadcasting. There are also access-wise operations that aren't reducing. One that we'll use in the tutorials is the softmax function. The softmax function takes a vector x and creates a new vector according to softmax of x is equal to e to the xi divided by the sum over all e to the xj. Let's see what this means. First, we calculate e to the x for each element. Then we sum the elements up along a specified dimension, for example, along the column dimension. Last, we divide every element by these sums. The softmax function has 3 important properties. First, the entries sum up to 1, so the results can be interpreted as a probability distribution. Second, if one value in the input is significantly larger than the others, say larger by 6, the result will be close to a one-hot vector, where only this entry is 1 and the others are 0, since the exponential function boosts large values over proportionally strong. Third, in comparison to a hard max function that sets the largest value to 1 and all others to 0, it distributes the mass more smoothly if the large values are close to each other. Even though the softmax function is no reduction, it needs a specified dimension as it is a vector-to-vector calculation. Along the specified dimension, it will create values that sum up to 1. Along the other dimensions, it doesn't have this property. Another similar case where you need to think about axes is when concatenating or stacking tensors. Let's say you have 3 4-element tensors, u, v, and w. You can use torch.stack to stack them to a matrix. If you stack them with dim equal to 0, you'll get a 3x4 matrix, where the vectors are the individual rows. If you use torch.stack with dim equal to 1, or torch.stack with dim equal to -1, you'll get a 4x3 matrix, with vectors as the individual columns. The position of the newly introduced dimension 3 is given by dim. For torch.stack, all tensors to be stacked need to have the same shape, so that the resulting tensor has block form. The similar torch.cat doesn't introduce a new dimension, but glues the tensors together along an existing dimension. We've mentioned before when we extracted the 3x3 matrix R and the translation vector T from the 4x4 tensor T, that it is beneficial to extract T with slicing, so that it is shape 3, 1 instead of 3. This is practical here. If we wanted to concatenate R and T again, we can do so using torch.cat with dim equal to -1, since they have the same number of dimensions. We've hinted on broadcasting when talking about the importance of one dimensions. Here, we'll finally see what all the fuss is about. In its simplest form, broadcasting follows this idea. Let's say we have a 4x3 matrix A and a vector B equal to 1, 2, 3. B has the same number of elements as the rows of A, and we might want to add it to each row individually. To do so, we need to broadcast it from its current shape 3 to the shape 4, 3, i.e. to the tensor 1 to 3, 1 to 3, 1 to 3, 1 to 3. Broadcasting in PyTorch allows us to do just that. First, we'd introduce a new one dimension to B and get it to shape 1, 3. This means interpreting the vector B as a matrix with one row. We have several options to do so. Using non-indexing, b.unsqueeze, or b.reshape are all equally effective in creating the new shape for B. Now, if we try to add A and B, PyTorch automatically broadcasts B to shape 4, 3 by duplicating the row. If we had B equal to 1, 2, 3, 4 instead, we could do the same trick to add B to all columns of A. First, we'd compute b.reshape to shape 4, 1, so that it is a matrix with one column, and when computing A plus B now, it is implicitly broadcasted to shape 4, 3 to match the shape of A. In general, the rules for broadcasting are the following. First, for two tensors to be broadcastable, all dimensions need to be identical or 1. Second, along these 1 dimensions, the tensors are duplicated to match the shape of the other tensor. And third, dimensions are aligned from right to left. If one tensor has fewer dimensions, 1 dimensions are added on the left. With this last rule, we could have left out the reshaping when adding B as a row vector to A. The shapes 4, 3 and 3 are broadcastable as they are aligned from right to left and ones are prepended to match the number of dimensions. Let's look at another example. Say we have a batch V of vectors, a tensor of shape n3, and we wanted to normalize them. We can compute the norms for each vector by using norms equal to torch.linearc.vectornorm with dim equal to -1. The result is of shape n. We can unsqueeze it with norms.reshape to shape n1. Now it is broadcastable and we compute V normalized as V divided by norms. However, we could have saved the intermediate step by using keep dim. This way, the calculated norms directly have shape n1 and are broadcastable against V. Another use case for broadcasting are each with each operations. Let's say we have a 3-element vector V and a 2-element vector W. If we want to compute the product of each element of V with each element of W, we'd get 6 elements in total. We can organize them in a 3x2 matrix where the entry ij is made up of Vi times Wj. This is called the outer product of V and W. You can see that it's basically just the pointwise product of a broadcasted version of V with the broadcasted version of W. Concretely, we can calculate this by reshaping V to a 3x1 column vector and W to a 1x2 row vector, followed by a broadcasted multiplication of the two. Broadcasting is an incredibly powerful tool. Together with the indexing, reshaping, and reduction techniques we've seen so far in the series, we already have sufficient tools to solve almost any problem in the whole series. If you try to do so, however, you'll see that these methods can quickly get a little cumbersome. Let's look at the most classic tensor-tensor operation, matrix multiplication. Given two matrices A of shape ik and B of shape kj, the matrix product can be formulated like this. For each row of A and for each column of B, calculate the pointwise product of the row and the column. After that, sum up along the column dimension of A, which is the row dimension of B. We've seen before that each with each calculations can be computed by expanding with 1 dimensions and doing a broadcasted multiplication. For the first step of this problem, we'd calculate C equal to A.reshape to ik1 times B.reshape to 1kj. Let's think about what that actually means. Multiplication is pointwise, so this is C at ikj is equal to A at ikj times B at ikj. But the last dimension of A just comes from duplication by broadcasting, and so does the first from B. So this actually reads as C at ikj is equal to A at ik times B at kj, or Cikj is equal to Aik times Bkj in math notation. Now all that's left to do for matrix multiplication is to sum up along k. We can do that in PyTorch using torch.sum. We might also want to compute batch matrix multiplication, where A has shape nik and B has shape nkj. We could compute this as shown here. In this example, we see all typical elements of a tensor operations. Some of the dimensions, I and j, are present in one of the inputs but not the other and are worked on in an each with each fashion. One dimension, k, is present in both inputs and is missing in the result. After calculating the pointwise product of the aligned vectors, the dimension is contracted by summation. One dimension, n, is present in both and is just used for a batched for each calculation. PyTorch has a method to cover all these cases in a really concise manner by using the Einstein notation with torch.einsum. The method takes an equation string and the tensors that are used in the operation. For our case of matrix multiplication, the operation would be torch.einsum with the equation string ik, kj go to ij, and the operands a and b. The batch matrix multiplication would be computed as torch.einsum with nik, nkj go to nij, and the operands a and b again. The equation string directly follows the rules we've seen above. If a letter is present in one of the inputs but not in the other and kept in the result, like I and j, the other tensor is unsqueezed and broadcasted to include the dimension. If a letter is present in both inputs but not in the result, like k, it is contracted. And if a letter is present in both inputs and the result, it is treated as a batched for each dimension. In the same way we used the ellipsis operator before during indexing, we can use it here as well to account for any numbers, or none at all, of prepended batch dimensions. With torch.einsum of ellipsis ik, ellipsis kj go to ellipsis ij, we can cover both the batched and the non-batched case simultaneously. Another example is the outer product we computed earlier. Without explicitly reshaping the tensors ourselves, it can be written as torch.einsum with I and j go to ij. Torch.einsum is incredibly flexible. You'll use it all the time throughout the series, and you'll already see a lot of examples in the tutorial notebook for this tensor introduction. The construction of the equation string can be a bit tricky at the start, but you'll quickly get used to it. And there you have it. We've covered the essentials of tensors in PyTorch, from basic creation and manipulation to advanced topics like broadcasting and torch.einsum. This knowledge isn't just theoretical, it's the bedrock upon which we'll build our understanding of AlphaFold. Next up, we have 2 more foundational videos on machine learning basics and the attention mechanism. After that, we'll dive into AlphaFold specific modules: feature extraction, the evoformer, input embeddings, 3D geometry, the structure module, and finally, putting it all together. But learning is an active process. That's why each video comes with a Jupyter notebook. In today's notebook, you'll work with all the tensor operations we've covered. As the series progresses, you'll use these skills to implement each part of AlphaFold with guidance and automatic checks to keep you on track. If you're ready to turn this introduction into action, head over to the accompanying notebook. And if you found this video helpful, give it a thumbs up and subscribe. That way you won't miss any part of your AlphaFold journey. Happy coding!